to talk about the alternating series test. So the first thing you want to know is what is an alternating series. And what that is going to be a series of the form n equals 1 to infinity of negative 1 to the n, an, or sum from n equals 1 to infinity of negative 1 to the n plus 1, an, where and a sub n, is going to be positive or non-negative rather, for all n greater or equal than 1. This means for all. Normally I don't write that kind of notation, but let's leave that there. All right, so what is the theorem going to say? Well, the theorem is going to say that for this one, that if the series is alternating, let's say sum from negative 1 to n of an starting at 1 all the way to infinity is alternating, then we're also going to need that a sub n be greater than a sub n plus 1 for all the n's, meaning the series is decreasing. If you look at the absolute values, it's going to be decreasing, and limit as n goes to infinity of an is equal to 0. If these three things happen, then the series is convergent, or the series converges, I should have said. Now, notice that the way I stated it right here, I'm assuming, really I didn't say it, but I'm assuming that these guys are positive. Now, this is true also for the series with the n plus 1. What is the difference? Well, this one is starting with a negative term, this one starting with a positive term, but they are both alternating. So as long as you have the signs going plus, minus, plus, minus, plus, minus, and all the terms are, well, you're adding and subtracting terms, then if these other two conditions are satisfied, mean that the sequence of the coefficients is decreasing, and that the limit as n goes to infinity of n goes to 0, then it converges. So now a contrast from the divergence test. So divergent test, if you remember, so your divergence test, that was if limit as n goes to infinity of the an, an is not equal to 0, it diverges, the series diverges. So remember that I told you that the limit being 0 does not imply convergence. Now, in the alternating series case, it is true. So, but you got to be careful to remember that if you take the limit as n goes to infinity and you get 0, it only works if you have an alternating series that is decreasing. So you got to be very careful with that. So some people get confused because, you see, we get used to then taking the limit, finding 0 and saying, oh, well, then it converges. No, remember that if it's not alternating, you got to go through your other tests, like the comparison test, limit comparison test, p-series, geometric series, integral test, and later in the module, we're going to also have the root comparison test and the ratio comparison test. All right, so we're going to do a few examples of this one, and then we will wrap this video up. This is a short one. So let's start with a super easy one. So the simplest you could think of, n equals 1 to infinity of negative 1 to the n over n. Now remember, I'm going to write it here because I'm going to delete, I'm going to eliminate it, but the sum of the 1 over n's, just positive terms, this one diverges, right? So that's not the same this time around, because what I'm doing, I'm actually writing out, say, negative 1 over 1, so negative 1 the next one is going to be plus, because negative 1 when n is equal to 2, negative 1 to the n is going to be negative 1 squared, which is positive. So when I have plus 1 half, then whenever I have n equals 3, this is going to be a minus and 1 over 3. And then when n is equal to 4, I'm going to have plus 1/4 minus plus minus plus, and so on and so forth. So this right here, this one actually will converge. So we'll show that by using the alternating series test. And it converges in a way that soon we will find out is not as strong as we think it is. But anyways, we're going to leave that conversation for later in the semester. So, so at the moment, however, we'll apply this theorem. So the condition is one is the series alternating? Yes, because the signs are going to be going plus minus plus minus. So that is satisfied. Second is 1 over n greater than 1 over n plus 1. So are the terms decreasing? And that is true, right? You just think about it. 1/2 is greater than 1/3, 1/3 is greater than 1/4, and so forth and so on. And this is easy to establish the form. Oh my goodness, I cannot talk. That the function f of x equals 1 over x is decreasing on 0 to infinity. That you do by taking a derivative. You get the derivative is negative 1 over x squared, which is always going to be non-positive. So it's going to be negative whenever you're away from 0. So you're going to have that this function is decreasing. So that gives you what you need. Delete this because we're just going to say it is decreasing. So good, we check that. And now the third condition is the limit as n goes to infinity of negative 1 to the n. And actually, take it back, the limit is just of an. It's 1 over n. So you see I wrote the statement of the theorem correctly, and now I compute my limit incorrectly. Here is just 1 over n. So you just do the an. The negative 1 to the n is not needed. You still could do an argument with like a squeeze theorem kind of argument, going with 1 and negative 1, but it's not necessary. In any case, so this limit we know is 0. So we have the three conditions necessary for the series to be convergent, or for the alternating series test to be applicable, are satisfied. And in that case, then the alternating series test tells us that the series from n equals 1 to infinity is convergent. And in a minute, we're going to talk about what types of convergence here. All right. All right, so preemptively added 2 pages just in case we need more. So let's do another example. So limit as n goes to infinity of, let's see, something like, oh, why am I doing the limit? I want the series first. Well, that was a fail. So let's start with the series. So the next example will be the sum from n equals 1 to infinity. Let's put a negative 1 to the n plus 1. And then let's throw in here a natural log. No, let's do an n over the natural log of n. Is that the one I want? Well, if it's not the one I want, it's going to diverge. So let's see how we do. All right, so let's take a look. And it may not even be decreasing, but let me think about it for 1 second. If not, I'll change the problem. Change my mind. I want to flip these guys over. We don't want an example that is not going to work at all. That's much better. All right, so let's take a look at this one. So, well, firstly, is it alternating? Well, at n equals to 1, you start with 0. So technically, we're starting this at n equals to 2. So it doesn't matter. But you have the negative 1. Now, the natural log is going to be positive. Once you're past 1, remember the graph of the natural log, the continuous function, on the interval from 1 to infinity. So when it's 1, you get 0. So that one was kind of silly to add it there. But then once you move to 2 and so forth and so on, this is positive, the n is positive. So the an, which is just this part, that's just an, that is positive. So we're good there. And now the question is it decreasing? So the next question is natural log of n plus 1 over n plus 1 smaller than the natural log of n over n? So is it decreasing? So that one is not as easy to establish if you don't do calculus. So here we're gonna look at the function f of x being the natural log of x over x, and we're going to take the derivative and see what the sign of the derivative is to determine whether it's increasing or decreasing. So this is a quotient, so I have to do quotient rule. Don't just do derivative top and bottom. It's not L'Hopital's rule. We're going to use L'Hopital's rule in a minute, but right now we're going to do a quotient rule. So derivative of the top, or derivative of the numerator, is 1 over x times the numerator, which is denominator, sorry, which is x, minus derivative of denominator 1 times the numerator, natural log of x, all over the denominator squared. And that's going to be just 1 minus the natural log of n of x, sorry, over x squared. And now when you look at the sign of this, the function at first is not going to be decreasing because natural log of x is going to be greater than 1 once x is greater than e, and e is 2.7 something. So when n, so this is going to be negative when n is greater than or equal than 3, or x rather here. In fact, it's just e, but I'm going to go to the integer, the closest integer, because, well, I really just care about the integers here, or the natural numbers, because those are going to be my indices, the ones I'm plugging in here. So that's going to be negative once I pass that 3. So technically, the first term doesn't exist because it's going to be 0. The second term, you would get negative 1 to the n plus 1. So you're going to have, when n is equal to 2, you're going to have negative natural log of 2 over 2, and then you would have plus, and you would have to have the sum from n equals to 3 to infinity, and then you'd have negative 1 to the n plus 1 natural log of n over n. Now, this right here, for this series, once you're past the 3, this coefficients a and are in fact decreasing. So technically I would have to do my analysis for this one, but since we only care about the behavior at the tail end of the series, being decreasing starting at a certain point is good enough for us. So decreasing, yes. So this is going to be f is going to be decreasing when x is greater than 3. So that works. That's good enough for us. The only thing we have left to show is that the limit as n goes to infinity of the terms, the an's, natural log of n over n, is equal to 0. Well, let's see if it's true. So this one right here, when you plug infinity, quote unquote, you get natural log of infinity over infinity. That's an indeterminate form of the form. Yeah, infinity over infinity. So that means that L'Hopital's rule does apply. So I can take my limit as n goes to infinity, take my derivative, 1 over n, over the derivative of n, which is 1. The limit as n goes to infinity of 1 over n is 0. So that tells me that the alternating series test does apply. And by the alternating series test, then I have that the series converges. Now, let me tell you one thing that I think would be a better idea to do. I've done it in this way, but it would be important, or easier, more efficient, if you will, to start with the limit. Start with the limit. Why? Don't do the decreasing, increasing, all that mess beforehand. Just take the limit. Why? Because if you get something that is not equal to 0, you can stop your problem right there, because the divergence test will tell you automatically that this series diverges, because the limit would not go to 0. So the strategy, which is not what I did, apparently I like to work extra, take the limit as n goes to infinity of an. So here's like a chart, flow chart. If limit is not 0, series diverges. If limit is 0, well, you're going to go through your steps. You still have to show an is greater than an plus 1. So meaning the sequence of terms is decreasing. And also you want to show that, well, your series you have to verify only that the series is alternating. The reason why I say that is because if you start checking this, let's say, but then you find that the limit was not 0, you just worked in vain because this was not necessary to verify. This series was not going to converge anyways. All right. The video is getting a little bit long, and I still have to talk about absolute convergence. Let me just at least define it. So absolute convergence. I'm going to talk a little bit about it now. I decided. So the series here, the ANs don't have to be positive. Converges absolutely. If and only if. I'm going to jump to the next page. N equal, but you see it was good that I added it. As n goes to infinity of the absolute values converges. I guess I could have put that over there. In fact, it fits. You see? Does it? Maybe not. Okay, fine. There you go. All right. So what it means is that, for example, these two series that I showed you, if you do the absolute values, you would have the series as n goes from 1 to infinity of 1 over n. This one diverges. So this does not converge absolutely, because you see this one converges, but the absolute values do not converge, or the sum of the absolute values. Same for this one. And so what do we call series that converge only the series itself, but not the absolute values? We say that if the series an converges, and the sum of the n equal 1 to infinity of the absolute values diverges, the series, this one in question, converges only conditionally, converges conditionally. And converging conditionally is not as good. Well, if you reorder and sum this conditional convergent series, if you reorder them, you can make them sum to different numbers. In fact, there's a theorem that you can make them sum to any number. So it's not as good. Absolute convergence is what we would hope for, but it's not always possible. Anyways, I think this has already been a long video, so I'm gonna stop right here. And I think I say that for every video, don't I? Yeah, probably. Anyways, so it's been a long video already, so I'll thank you for watching, and I'll see you in the next one.